This will be the second part of the nuclear chemistry lecture for AP Chemistry. We start the second part of the lecture with the slide that deals with the rates of radioactive decay. Now each isotope has a characteristic half-life, and that's the time required for half of any given quantity of the substance to change or react or decay. In our case, it's going to be radioactive decay. Now half-lives are not affected by temperature, pressure, or chemical composition. Now natural radioisotopes tend to have longer half-lives than synthetic radioisotopes. So if you're a natural element found on the Earth, you're going to have a longer half-life than something that's man-made. Half-lives range from the fractions of a second to millions of years, or even billions of years in the case of uranium. Now naturally occurring radioisotopes can be used to determine the age of a sample, and this is the process called radioactive dating. So you can figure out how old something is by the amount of radioactive isotope that remains in the sample. So here's a table of some half-lives of common radioactive isotopes. Uranium-238 has a half-life of 4.5 billion years. Uranium-235 has a very long half-life as well. And some synthetic radioisotopes, strontium-90 is 28.8 years, and iodine-131 is a fraction of a year. So you can just get an indication of how long things stick around. Now carbon-14 in the natural radioisotopes column is one of the most important half-life isotopes to know. It has a half-life of around 5,715 years, and the reason we use carbon-14 dating for a lot of scientific measurements is because humans have been around with written languages, or the pyramids and stuff like that have been around for around 5,000 to 10,000 years. So carbon-14 is a good way to date human relics. Now here's how carbon-14 dating works. A small amount of carbon-14 is present in the atmosphere along with carbon-12 and carbon-13. Now carbon-14 remains uniform in abundance because as it decays, it's replenished by cosmic rays striking carbon-14 and turning it into striking nitrogen-14, and it turns it into carbon-14. So the amount of carbon-14 in the atmosphere is pretty constant. So as a result, there's a ratio of carbon-14 to carbon-12 in a sample. It's very, very constant. Now plants use carbon dioxide in photosynthesis as long as the plant's alive. The carbon dioxide ratio will be the same in the plant as it is in the atmosphere. But once a plant dies, the carbon-14 that the plant has taken in starts to decay, and this ratio lowers. So the carbon-14 decays, and so the carbon-14 to carbon-12 ratio diminishes. Now the half-life again is 5,715 years. So after 5,715 years of being dead, a plant will have half as much carbon-14 as it should have when it was alive. Now wooden relics thought to be less than 50,000 years old are dated by burning the sample, and it releases the carbon dioxide, and you can figure out how much of it was the carbon-14 carbon dioxide or how much was the carbon-12 carbon dioxide, and then you can figure out how old it is. So radioactive decay is a first-order process, and we've had this formula before. It's the natural log of the concentration at some time divided by the concentration at the beginning, and that equals negative kT. Now there's another way to look at the formula. It's on your AP equation sheet. But anyway, N0 is the initial number of nuclei. Now we don't need to worry about concentrations because we're not going to be doing moles per liter. We're just looking at how many nuclei there are. NT is the number of nuclei after time T. So N0 is the initial, NT is after some time. And in radioactive decay, the rate constant K is the decay constant, so that's going to be the half-life number. Now the rate of decay is called the activity. That's how many disintegrations it has per unit time. Now the relationship between K and half-life is given by the 0.693 divided by the half-life T formula. So if you know the half-life, you can calculate K, and if you know K, you can calculate how many nuclei are going to be left after some time. And we're going to do a practice problem to make it all tie together. So what's the age of a dead tree stump containing 11.6 parts per million of carbon-14 compared to a living tree that has 15.2 parts per million of carbon-14? So we know the half-life is 5,715 years, so you can calculate K for carbon-14, and it ends up being 1.21 times 10 to the negative fourth per year. So we use that number in our next formula. We take the natural log of the ratio of the carbon-14 after a certain amount of time divided by the carbon-14 that the tree should have. So it's 11.6 divided by 15.2, and you set that equal to negative KT. And you do the calculation and you end up getting a certain number of years for your unit, which is 2,230 years old. Now, just for your information, 15.2 is the initial amount of carbon-14 in the tree sample. So if you cut that in half, you'd get around 7.6. So if the concentration of carbon-14 was down to 7.6 parts per million, we would know that it has gone through one half-life. So we should be able to see our answer makes sense. We're less than one half-life, or we're less than 5,715 years old, or the dead tree stump is less than 5,715 years old. Now here's another practice problem. What percentage of radioisotope remains after 8 half-lives? Well, that means we're going to cut the sample in half 8 times. That's 1/2 raised to the 8th power, which is only 0.39% remaining. Now we're going to change topics and talk about nuclear energy. There's two types of nuclear energy. There's fusion and fission. Let's do fusion first. Fusion is taking light nuclei, they stick together or fuse together to form heavier nuclei. Most, if not all, of the sun's radiation is produced by fusion reactions. And here's what happens. You take a couple hydrogens, you smash them together, you make helium. High energies are required to overcome the repulsion of these hydrogen nuclei before these reactions can occur, so these take place in the center of the sun. Now it just is interesting that you're using hydrogen 1 and hydrogen 2 and you're smashing them together to make helium 3. Now high energies are achieved by these high temperatures, and these are called thermonuclear reactions. So a hydrogen bomb is different than an atomic bomb. A hydrogen bomb is a thermonuclear explosion where you're fusing hydrogens together to make helium. In your normal atomic bombs, you're taking a radioactive substance and dividing it, or fission reactions, making the energy. Now, fusion of tritium and deuterium require about 40 million degrees Kelvin, or 40 million Kelvin, so it's very difficult to do. Here's deuterium, which is H2, the hydrogen that has a mass of 2, and tritium is H with a mass number of 3. You smash them together and you create helium 4, and you also spit out a neutron. These temperatures can be achieved in nuclear explosions. So if you want to blow up a hydrogen bomb or a thermonuclear bomb, what you have to do is you have to blow up an atom bomb. The heat of the atom bomb sets off the fusion reaction, and then your hydrogen bomb blows up. And that's what that bullet point says. An atom bomb generates the heat needed for the fusion of a hydrogen bomb. Now on the next slide we have the energy of the nuclear fusion reactions. A helium nucleus contains 2 neutrons and 2 protons for a calculated mass of 4.03190 atomic mass units. Now if you measure the mass of the nucleus, it's 4.0015 AMUs. So there's some mass that's missing. So where does this mass come from? This mass is converted into energy. So the mass between a calculated neutron and proton versus the actual neutron and proton stuck together is converted into energy according to Einstein's equation, E equals mc squared. And this is about 652 million kilocalories per gram atom. So that's a heck of a lot of energy just by fusing hydrogens into heliums. Now 1 kilogram of hydrogen fused into helium yields about the same amount of energy as burning 20 million kilograms of coal, so it's a lot more efficient, and that's why people are looking to create fusion reactions to run power plants and stuff. This could be a great source of energy, and it's relatively safe because the products of fusion are not radioactive, they're just helium. So we can't quite sustain the necessary temperatures yet. They have to use lasers and stuff like that, and in the movie Spider-Man, I think it was Spider-Man 2, where they had Doc Ock, he was creating this in his laboratory, so it's a good movie to watch if you want to learn a little bit more about the properties of fusion. Now we talk about nuclear fission. Nuclear fission is the splitting of a heavy nuclei into lighter products. Just as in fusion, there's a small amount of missing mass that gets converted into energy according to Einstein's equation. So here's how you start a fission reaction. You take the isotope 235, you smash in a neutron. The neutron sticks to the nucleus. The nucleus becomes uranium-236, which then breaks apart into the barium and the krypton, and then 3 more neutrons are produced, and those 3 other neutrons will go and smash with more 235, and then the process continues on and on and on. So notice the reaction needs a neutron in order to start, and it also produces 3 neutrons which continue on. And this is called a chain reaction, where you create a reaction and then products continue to make more of the reaction occur, and more and more and more. So it keeps going on until you run out of a critical mass of uranium-235. The critical mass is the amount that needs to be in one location for the chain reaction to sustain itself instead of fizzling out, and it's about 1 kilogram. Continuing on with nuclear fission, just a little picture of what it looks like. And nuclear fission power plants is what we have in Clinton, Illinois, right next to Champaign, Illinois. Nuclear power plants use fissionable materials, substances like uranium-235, to generate heat. Now the heat boils water. The water turns into steam, and the steam turns what's called a turbine, or a giant fan blade, and that fan blade turns a generator, which is composed of magnets and coils of wire, and when the magnet is spun in the coil of wire, or the coil of wire is spun in the large magnets, it creates electric fields, that creates the electricity. Now, the process of generating electricity from spinning magnets and wires is more of a physics topic, so we're not going to cover it in much detail here. Now, fission capture by uranium-235 occurs with slow neutrons. So when the neutron smashes into the uranium-235, it has to be going slow enough to actually stick instead of just bounce off. And so you have to use what's called a moderator to slow the neutrons down. And they usually use a graphite moderator or water as a moderator to slow the neutrons down so they don't bounce off the uranium-235. They actually stick. Control rods contain cobalt or boron plus other metals can be used to regulate the neutron capture. So you don't want all of the neutrons to be captured, only a fraction of the neutrons to be captured, so you can control the process. Neutrons escape the reactor, but the larger reactor it is, the less likely it is that the neutrons will escape. So there's a minimum size for a nuclear reactor. So you can't have a nuclear power car because it would just be way too large. So there is a size factor that limits how small the reactions can be, or the reactors can be. And that's what the last little bullet point says. You cannot have an atomic powered car or an atomic powered plane because it's going to be too big. Now, nuclear fission reactors look like this. Again, you have the reactor core. There's a confinement shell, usually made of reinforced concrete and steel, and then there's a pump to transfer the hot water into the place where the steam is generated, and that keeps the reactor core cool. If it gets too hot, there could be a steam explosion. There's not going to be a nuclear bomb explosion, but there could be a buildup of too much steam, and then the steam blows apart the containment field. And that's what happened in Chernobyl, which I'll talk about in a little bit. But anyway, the heat from the reaction goes into the water turns into steam, and then the steam turns the turbine, and then it goes on and produces the electricity. And then the water has to be cooled, so there has to be some sort of reservoir for the water to get cooled down. And for us in central Illinois, we use Clinton Lake, and that's why the lake doesn't freeze around the power plant, because it's pumping in the warm water from the nuclear reactor. Other places have cooling towers where the steam is just released to the air. Now here's some nuclear safety issues. A reactor is not a bomb. There's not a critical mass of uranium present. The worst accident that we've had on the Earth is Chernobyl, and there was a core meltdown. And what happened is that they pulled the control rods up, and there was too much steam in the reaction, and the reaction blew off the top of the containment field, and then air rushed in and caught the control rods on fire, and then the nuclear reactor was on fire, and then the smoke was billowing all this radioactive material all over the place. So you could have other problems like a leak in the coolant system, and that's what basically happened at 3 Mile Island. There was a pump that failed, and then there was some radioactive water that was released, radioactive steam that was released, but it wasn't hardly any radiation in the environment, though people kind of freaked out. Now, contrary to popular belief, nuclear power is the safest significant source of energy being used right now. It gets a bad rap, but it's the best energy source out there. France is like 90% nuclear power, and they don't have any problems with it, so no use to freak out about it. Think about how many people die in a coal mining accident or natural gas explosion. So some people are like, "Oh, nuclear power is very dangerous." No, it isn't. Now, the only problem with nuclear reactors is the disposal of the radioactive waste. The fuel rods can accumulate impurities and they have to be disposed of. And the waste is first stored underwater at the plant site where radioactivity decreases, usually a few months. And then the options that the United States is looking at now is putting them in Yucca Mountain, which is out in Nevada. It's just a salt mine, so you can just bury it underground. But the problem is that if the containment tank ever does leak, it could pollute the water table. Another issue is thermal pollution. Like I said, Clinton Nuclear Power Plant puts all their hot water into the lake, and so the cooling water is heated, and then when it returns to the environment it might cause the oxygen to come out of the water because it gets too hot, and then the fish could die because they don't have anything to breathe. And it turns out that this issue is actually less of a problem. The fish at Clinton Lake actually like the warmer water, so they spawn more and they have more fishies. So that's basically the disposal of radioactive waste in nuclear reactions.